And some of us are locked out of the storm screen.
All right. So yeah, thanks for coming. Great to see you all.
Joining us.
I'm Ambrose. I'm at Indiana University right now, and like literally right now in my office, and I work on typed Clojure. That's an optional type system for Clojure, and today I'm just going to show you some of the developments that have been happening over the last few months and moving it away from optional typing to what's called gradual typing and some different things in between.
Awesome.
All right, so let's try this magic trick again. Hang on. Screen share, Ubuntu. Is this working?
Yeah, it is.
All right, so let's start from the top. This is what this project looks like. This should look familiar to everyone if you use Clojure and Line Engine. It's just a normal Clojure dependency. So this dependency isn't lying. Like the Clojure compiler is used to compile all our code that core.typed generates. So core.typed basically works with real Clojure code, and it compiles it with the same compiler. And the interesting thing that we've added here, well, we've added two interesting things. Well, we have the latest core.typed version, and notice this is just a jar, so there's no reason to be frightened away from even experimenting from this. So it's just Clojure 1.7, and we have an extra jar. And if you notice, if we go to, before I explain this injections line, I'll show you that our typed, a new way of writing a typed namespace. So we have some lang metadata here. So if you've ever used Racket, you'll know that you can extend the language to make new languages. So in effect, I've made a new language called core.typed with this directive here. And what this really means is that once someone calls the load function, and the require function does call the load function, as in clojure.core/load, load is monkey patched to then, for example, if we load Houston talk problem typed, then core.typed gets to choose how to load it. And the way that we monkey patch this is with these two ugly lines here. We have this namespace load and a suitably scary name for what's actually happening. So this isn't really supported per se by, like this isn't really a good idea, but it works for now, and this is the way it works. So it's good to know what's actually going on under the covers if you end up integrating typed Clojure into your tool chain. If something else is monkey patching load, then you're going to have to think of something else. Anyway, that's some of the boring stuff out of the way. But in effect, what this means is that we can call require on this namespace, and the type checker will actually run. And I think I've put a type error in here. Oh, yeah. I don't have a very good computer, and I'm 1 on a Hangout, and 2, I'm recording this on my machine. So core.typed is extremely slow, but only about 10 times slower than what you're seeing in reality. Okay, so yeah, so what I just did, I just called require, and core.typed got automatically called. So let's just have a quick overview about what's in this actual, what's in this namespace. Well, we have 3 annotations. These are static types. These are descriptions for the values that these vars can inhabit. So, for example, use A is a function of 0 arguments, and you can see it's a function of 0 arguments, and it returns an int. So we write with an open vector. We write an arrow, and you may have also seen this syntax. These are absolutely equivalent. I just like using the keyword arrow and the return type. So what core.typed is doing, it's basically type checking this var, making sure it's an int, and then the return type is an int, and then it checks that everything's consistent. So this is what's called an expected type, or an annotation for a var. So when we check this var, we're going to know for example, in this last one, the type for f will be informed by our annotation. So that this var useC is a function of one argument. Its one argument takes another function of one argument. So for example, inc is a function of one argument that takes an int and returns an int. And then all it does is it passes off to this other mysterious thing, which we will talk about in a sec. So any questions on what I've said so far?
No.
Can you go over line 15 again?
15. Okay, so this is an annotation. So just so we're all on board for what the actual value is that we're annotating, use C is a defin. It takes one argument, a function f, and it passes that function on to something else. And now's a good time to show you what this something else is. So this u is this alias over here. So let's go to problem untyped. And problem, so laggy, wow. Okay. Here is C. So C takes in a function and just passes it a string. So you can see all this is doing is just passing this function along. So for example, if we call useC on inc, this inc flows to here, flows to here, flows to here, flows to here, and then we increment a string. Okay, so that's the value. So the type is a function of one argument. So what I've got highlighted here, this is basically this part. It's a function of one argument. It takes in a function of one argument. So this f is an integer to an integer function. Then this entire thing returns an integer, which is the result of this call here.
Okay, I have a question.
Go on.
All right, so on line 15, you have this vector, and this vector has 3 elements in it, right? And is that
yeah, 1, 2, 3, sure.
like the whole vector itself is the annotation for useC, but the first item in that vector is itself another definition for the argument after being passed in.
So in the same way that functions are first class, in that we can pass functions as values, like types are first class here. So we can, function types, we can arbitrarily nest them, basically. This is a function type within a function type.
Can you label? Could you have labeled that? Like, could you take that type and call it banana and then label F?
Oh yeah, sure. Let's do that. That's a great idea. So we have this feature called an alias, a type alias.
Banana.
N1, slightly better than banana. Was banana. This is the documentation string. All right.
Now you say it.
Okay.
Thank you for doing that.
Yes, and what you suggested is basically how I used typed Clojure in the real world. Like if I have these nested annotations, as you probably noticed, they're almost unreadable, and probably in any language this is a good idea. But now I have code that I've never run, so let's see what happens.
What could go wrong?
Unannotated var. Oh, yeah. Is this what I expected? Yeah, because this is called problem. So it's a problem. It doesn't compile. Okay, excellent. No, this is perfect. I think, let me just consult my README. If you go to this, this repository, you'll see this README. So where are we? Okay, so the whole point of what I'm trying to say, here we have, up the top is untyped, which means it's not type checked with typed Clojure. But what we have down here is a typed namespace, and you can tell because it's being type checked by core.typed. So there's this language boundary. If you think about all the places where these two lands have to communicate, where typed land and untyped land have to communicate, you can think of a language boundary that it has to cross at some point. So gradual typing is all about managing this boundary. And maybe this picture might help a little bit, even though it's an ASCII, terrible ASCII drawing. So, and it's inverted. So we have our typed module, we have a language boundary, and then the dependency is that the type module depends on the untyped module. So there's going to be values flowing this way. Is that right? No. Well, both ways, because we have higher order functions. Yeah, already I'm confused. This is a subtlety with gradual typing is going back and forth, and of course the trick is always with the higher order things. So higher order functions make things difficult. Okay, so the question is, how do we safely communicate between the typed and the untyped namespaces? So for example, what's the safe way we can import A, which is an int? Clearly this inc is going to work, but we need to communicate this to typed Clojure. Okay, so the first approach is under approach 1, typed, approach 1, untyped. Okay, the first approach is pretty, it's either dumb or it's smart, but it's definitely a lot of work. The approach is basically to just change untyped to be typed. And if we look at our little diagram, now typed land has both typed and untyped in it, and untyped is now a bad name. But there are no language boundaries to cross, so there's no interesting questions to answer. So what effectively happens is core.typed will get to this line and then type check the other one. And then the annotation for A will show up over here. And then core.typed will know that A is an int. And let's all cross our fingers and run this. And there should be a type error if I remember correctly. Or at least, yeah, okay. I was going to claim that this is unreadable because the font is so big, but usually working in Vim like this, it's unreadable anyway. So we'll just work with it. Okay, so the error, what's the best way I can present this? What the error is actually saying is this line here. In untyped land, we've annotated f to take in a function that takes in a string and then returns an int. So this function here, that's exactly how we use it. But the problem is, when we use C over here, we give it a function that takes an int to int. And an int, if we need a function that takes in an int and we give it a function that takes in a string, then we have a problem. Okay. How do we fix this? Well, I guess let's just fix it. If this is kind of, what's the best way to fix this? We could do this. We could make our untyped thing. We could change our untyped code. Ugh, I'm getting some feedback. Maybe, is it possible to turn me down a little bit?
Sure. You just mute.
Testing.
I could just mute.
Until we have a question.
Yeah, I guess I could do that. Let's see. I'm just going to mute our room until we have a question, okay?
Okay. Okay. Testing. I'm muted. Must be. Good. Okay. Thank you. What was I doing? Yeah, sorry. The feedback really threw me off. Okay. The problem was that we've got a function from int to int, and we're passing it to a function that expects a string to int. So we could just change it, I guess. Right, that worked. Okay, anyway, there's no more reason to dwell on this particular example because the next example is more interesting. Okay, so in our second example, we're going to still have the typed land, the typed namespace be typed and the untyped namespace be untyped, But what we're going to do, we're going to use runtime contracts to make sure that any values going across this language boundary are conforming to the static types at runtime. Okay, so let's open another thing. We're going to approach 2 and untyped, approach 2, untyped. Okay, notice untyped is exactly the same as the problem. So we haven't converted this. This is really an untyped module or a namespace. So let's just get it out of the way. But the typed one looks slightly different. So what we've done is import these 3 vars. So we have A here, and if we had to give it an annotation, it would be that it is an int. And perhaps it's best if we comment out these lines and work one by one. Okay, so we have a annotation for A, as in this, and it's an int. So the way we use A is that we increment it. So what type Clojure is going to do, it's going to assume that this is in fact of type int, even though it hasn't type checked it. But what it does, it effectively generates this code. So it's going to cast the value of A to the type int. And then type Clojure knows that it's safe for inc to be passed an int, and that when it does return an int. Okay, but we don't need this. Hopefully we can just require it. What have I done? Oh. Okay, so something happened, it compiled. So the magic really happens at runtime. So here's some magic. If we call use A, it's going to get the value 1 and increment it. Okay, so if we actually call it, we get 2. And actually this example, this is where the interesting parts end for this example. So let's move on to the next one. So B is the function inc, and it's an int-to-int function. So the way we use it, you can see we're passing it an integer. And again, if we type check, and then we call use B, what's going to happen is that we're going to increment 1, okay? We got 2 again, okay? But what happens if we increment, for example, A? So what actually happens here is that we get another one of these huge type errors. What's actually happening is that we have this call B, passing the string A to B, and what it's complaining about is that we have a static type error that the domain, the expected domain is int, and the actual thing that we've given is the string A. So the interesting thing about this, and the reason I'm dwelling on it, is that this is a static type error. So type Clojure understands that assuming that B is of type int to int, then this is an ill-typed form. Okay, so let's say that we're actually using B correctly, but we change B to be something different. So it has to be an int to int, so it takes a number. Let's just say it just returns some bad value. Okay, so just to predict what's going to happen, when type Clojure imports this, it imports it like this. It casts B to an int to int. So it enforces that at runtime we only give it ints, and that at runtime B only returns ints. But let's delete this correctly. stop giving everyone seizures. Okay, so actually what we're expecting is that at runtime, it doesn't actually return ints, it's going to return a string. Okay, so let's actually type check. Okay, so, and we use it, we get an even crazier looking error in a large font. Okay, so we get, this is a runtime error, so we get some interesting information. So the line number looks good, line 14.4, so this is where it happened. We get this thing called blame, a positive blame. So the positive blame is really who's to blame for passing, or another way of saying it is this contract failed. Intuitively, who's to blame for this failure? Well, what's actually happening here is that we're blaming the annotation of B. We can't quite read that, but it's annotation for Houston talk approach to B. And that is here. So what it's saying is we've made incorrect assumptions about B, that it's returned an int, and it's actually returning a string. I'm not sure if that got through. Maybe a good question, time for questions, if there are any. None?
Yeah, so actually Jared had a question.
Okay, shoot.
I'm
over here.
The ginger.
Wow.
Yep.
Thanks.
I know, sticks out.
I saw the positive blame, but there's also a negative blame in that message.
Yeah.
What was that negative blame?
Okay. Let me get into the mode where I'm explaining this. I think I learned about it last week properly. Okay, I think I need some long arms to explain this, so let me show myself on screen. Okay, so let's set up this situation. So we have our language boundary in the middle. Actually, ignore that. Just think of someone, two parties in a transaction. So say I'm giving a value to the Houston Clojure Group. Okay, so I am the, or in other words, the Houston Clojure Group is receiving a value from me, and the Houston Clojure Group asserts that it has to be an integer. So the Clojure Group is it's the negative blame, and I am the positive blame. So say the Houston Clojure Group wants a value of type int, and I give a value of type string. What the theory of blame says is blame the positive party. So I get blamed. If is that another question? Am I going too quickly? No.
Could we interpret this as a positive party is the one doing the action, whereas the negative party is the one receiving the action?
Did you hear that?
Yeah, I heard it. I think that's right. Again, the interesting case is the higher order case. So, okay, consider this. You want a function int to int from me. Okay, so if I give you a function, great, I can't be blamed for giving you a function. But say you pass the function a string. So now the positive and negative parties are swapped. So if you pass it a string, that's a failure because I gave you a function that should be passed only ints, and you used it incorrectly. Conversely, if you actually give the function an int and the function returns a string, then the blame is the original. The blame is as it was originally. So I am to blame if that function returns the wrong type. Did that make any sense?
Did the person who made this up, did they have a political science background? The reason why I asked that is because it's analogous to positive and negative rights. That's a different story.
A positive and negative what?
Rights. For example, you guys' constitution is a constitution of negative rights. Like that's something else.
Okay, I don't.
Question. So is all this happening at compile time?
So
And then like this, or I guess you showed some stuff that happens at compile time, and there's some stuff that happens at runtime, like a casting.
yeah.
Like the
So-
casting happens at runtime, right?
So what's happening at compile time is that the code that does the casting is inserted. And then at runtime, the cast is actually executed.
And does this work for Clojure script?
No.
No,
No.
it's not.
But it would probably take a good week of development to get it working. I've made sure that there is a good compatibility story of the. The main issue right now is that the Clojure script compiler has diverted from when I used to have support, and also I don't know how to deal with interop with JavaScript. So I could harvest TypeScript annotations, but I just haven't done that yet.
Okay,
yeah.
let me know if you need help with that.
Yeah, email me. I need help right now because that
Also,
is the
the
question I get all the time.
Okay, the Google Clojure compiler has like these type annotations as well.
Yeah, I think those are just as easy to get to as the TypeScript ones, maybe. But yeah,
Yeah.
I'm aware of that. And the Google Clojure compiler seems more relevant to Clojure scripters, right? You'd use more of the features in that.
Yeah.
Yeah.
I guess I'm just thinking that you don't want a lot of this casting happening at runtime in JavaScript. That's going to eventually, eat you up for performance reasons.
Yeah. So this casting stuff, it's well known that it is a massive performance hit. In typed racket, there is at least an 8 times slowdown in typical programs. I mean, that's the minimum. Sometimes it's hundreds. It's pretty crazy. So my philosophy is this is a dev time tool. The contracts work especially well in combination with generative tests. If your generative tests are testing all the different ways you can execute your program, and all of them are protected by contracts, theoretically, you're eventually going to weed out all the contract failures that might happen at production. So, in other words, disable the contracts in production, which is simple to do. You just comment out the core.typed language, and it just compiles as normal Clojure. Or, yeah, there are other ways of doing that. Yeah.
Cool. Okay, thank you.
That's all right. All right. So we have, this is our positive blame. Where were we? Yeah, so B is a, oh, could you mute me, please? I'm getting some feedback.
Yeah.
Thank you. All right. No? Is that better testing? All right, cool. Okay, so where were we? We have a function that actually returns a string, and we're expecting a function that actually returns an int. When we call this thing, we get positive blame on the annotation of B.
Hey, Ambrose, can you put the code example back up,
Whoops.
please?
Yeah.
Thanks.
How's that? Okay. So let me repeat that. What did I say? Okay, so here if we call use b, it's going to, our invariant is that this is supposed to take in a number and return a number. It actually returns a string, so this cast here will fail. So we blame the annotation for b. And the third way we can demonstrate this is with this other function c that takes in another function and passes it a string. So what this use c is actually doing, it takes in a function. So here's an example usage for use c. Inc takes in a function from int to int, passes it to f, and then we increment a string. So this would probably be some sort of class cast error at with untyped code. But what's actually going to happen is that we're going to cast this to this type here, and we're going to get a different error. So let's see what that is. Oh, I haven't compiled it. Stop. Oh, did I annotate use C? Let's cancel that. Nope. Okay. Okay, so compiled. So what happens if we pass it inc? So we get another blame. So we blame again the annotation for C. And why is this? So in Racket, these error messages say stuff like the domain of the range of the domain of some annotation. Like, for example, what's actually happening here is that this part of the annotation, this part of the annotation is failing because we're passing a string where it's expecting an int. What the error message would like to say, what I'd like it to say, is this part is failing. But what's actually happening is that it's saying, this entire annotation is wrong. So yeah, I guess the point is that using blame and a contract system, we can check the values of things like functions and use them in higher order ways, and then we can avoid these bad error messages, and we can also avoid violating the invariance of the static type system. So f really is a function. C really is a function that returns an int, and if it's not, then we will get a runtime error. Okay, so that is the approach. Let me go back to my picture, where we have typed land and untyped land, and communication between them, and whenever we import things from untyped land, we add a contract at this point. So whenever we cross this boundary, our typed code is also contracted. Okay. Yeah, so yeah, the high level way that this was done was, or a little bit more into the details, we use the untyped var form to annotate A, and then this is basically the same as casting every occurrence of A. Okay, so this next approach is something I implemented, I don't know, like 12 hours ago, so I'm actually not sure if it's going to work, but it's a cool idea. So we had previously, if I go back, we had the situation where we made both the things typed. We made both, one thing typed and one thing untyped. So the other natural combination is that both things are untyped. So, well, what's the point of moving from typed to untyped? What about all that work that we did for annotating this namespace? Well, what this approach here does is that it throws out static checking, but replaces it with fully dynamic checking. So all the annotations on the vars will basically be converted to casts at runtime. So let's just show that. approach 3. Okay. Okay, so the magic keyword is the runtime check feature. So notice this is the normal thing that we had before, but now we have an extra entry in our metadata map for the NS that has a core typed entry, and in that entry there is a features keyword, and then we have a set of features. And this feature is called runtime check. And what it does, it basically collects these annotations and then converts use A, for example, to something like this. To a cast to int. So what's actually happening is this use A is enforced at runtime instead of compile time. So there is actually no compile time checking going on here. This runtime check completely elides any static type checking, which seems bad, but kind of if I go back to our diagram here, kind of the situation that I'm imagining is that untyped is kind of too complicated to just port in one go, and we need some way to experiment with the interactions between these two namespaces. So it's kind of restrictive having to have a well-typed program at every step of your development process. So I'm imagining, say if you're starting and you have your type namespace and type land, and then you're like, well, it would be nice if I disabled type checking but still had some of the guarantees that came with type checking. So this ends up being contracted. So notice that there is no longer any language boundary to cross. So we don't have to answer the question of how do these two namespaces interact, because it's only the top level annotations that are being converted. So let me be more concrete about that. What was I talking about? Yeah. So yeah, this top level annotation is being converted to a cast, but notice that we don't care about the type of A here. This can be anything. This is a dynamically typed program, and this is not being type checked. Okay, so let's run this before I ramble any longer. String doc, what does that mean? Approach 3. I will frantically delete code until it works. Oh, something's happening. Past def. Oh, that's it. Whoops. Thanks, Tools Analyzer. Okay, so we're compiling this. What's actually happening is we're inserting these casts at runtime. We're inserting runtime casts, but we don't have any static type checking. So theoretically, these are actually bad examples. What's a better example? Let's just get rid of this. Let's make a new thing called takes int. It takes in an int, and then does the boring thing. Okay, and then what we're going to do, okay, we should compile this first. And I should note that this cast insertion and any type checking that happens only happens when I require something. It doesn't happen when I use eval. So this is kind of a shortcoming of the current approach. Hopefully it'll be fixed at some point. Okay, so the interesting part is, okay, we can call take int and Oh. I have to compile this again. Calling int on an int is no fun. We've got to increment it. Come on. All right, so it type checked. Okay, so we can pass 1 to this. Okay, that's fine because the cast it's going to pass the input cast. If we pass nil, we should get a cast error. What's it? Okay, so if we don't really know both the parties, we just put cast as both the blame and the the positive and negative blame. So it's basically the imaginary cast that happens around here that corresponds to this gets blamed for this annotation. So notice that actually in the other modules, if we ran this using just a val, this would run because there's no contract on this input. But now there is, even though it looks like a statically typed thing. This is actually being checked at runtime. Yeah. Okay. Any questions on that one? I think I made it quite convoluted.
Questions? Anyone?
Did it make any sense?
Yeah.
Okay. Well, that's promising since I only just implemented it, and this is the first time I've described it to anyone. But the high-level overview is instead of static typing, we have dynamic checking for everything.
Yeah, I think it's. I think that's a really interesting idea. I mean, I'm doing a thing on OCaml right now, and having to have types everywhere all the time is troublesome for newbies sometimes. So
yeah, and it gets even worse with typed Clojure because one of the activities you'll be doing over and over is starting from an untyped thing and moving to a typed thing. So you won't even be like in OCaml. You won't even start with a typed thing. You'll start with an untyped thing, and then you have to recover the static typing. So I think using this scheme here, contracts has a great property where you can add one contract. So in schema, you can add one contract and you will immediately get benefits. So this kind of steals some of that idea from contract land. And that's something that you don't get with static typing. You have to do a lot of work before you get any benefit from porting a untyped thing to be statically typed. So that was some of the motivation behind it. Yeah.
Cool.
Can you do maps and like if I have a map and I want it to have like 3 keys and those 3 keys all need to be strings?
Yeah.
Can I?
So
I can specify for that.
yeah, you can do that. The problem is right now that the contract system can't generate checks for it yet, which is why I've been using ints. But actually, in all of my talks, heterogeneous maps are my favorite subject because they're super cool. You can assoc, dissoc, merge things, and the type system will understand them. And I'm pretty much done with where I got to with my content. Do people want to see how maps work? A little demo with that.
Yeah, I wouldn't mind seeing a map
There's
where
a lot of head nodding.
All right,
so
let's do it.
Sounds like
it's
a good thing.
To give you context, if I have like a function that is problematic, I'll put in like a pre-post condition and I'll write predicate functions that are just checking like map keys.
Yeah.
But that's
yeah.
happening in runtime, and it'd be great if there was a tool that could catch that.
Oh yeah, it can catch it. All right. So let's.
I'm gonna mute you again. Okay.
Oh yeah. Thanks.
I'm gonna mute us, I guess. No, don't. I'm not gonna mute you.
Maybe unmute me because I didn't hear any feedback. I'll just bother you once.
Okay.
Once it happens again.
Okay.
All right. So Houston talk dot hmap. Is this where we are? Hmap. Lang. Core.typed, and do we need anything? Sure, let's grab require Clojure core typed as T. Actually, let's write a function. What's this function going to do? It's going to take in some map. It's going to take out its A and B key. Let's do something more interesting than incrementing. Let's associate the C key with the A key. No, that's not what I want. I don't know. I'm being too ambitious. All right, no, I can put in an addition here. Yeah, that's what I want. Now it's much better. Okay, so this is, yeah, this is a good example of, voila, it is now untyped and will run faster, which is a super cool property, actually. Okay, so this is going to do what? It returns Z, C3. I'm picking up American pronunciations. Oh no, it's happening.
We're infecting you.
Yeah, I've had to write papers in American now, but it's a little different. All right, so let's write an annotation. F takes in some map n, m, and returns some map. These are terrible names. A and B. Oh, this is even worse. Let's call it input and output. Okay, so let's write an alias for input, and has A and B entries, which are ints. This is how we write that. Okay. The output has a Z entry, which is another map. Fine. And Z, what was it? No, C int. Okay. I think I'm feeling good about this. This should just work. Oh, but well, of course it worked.
There's no demo like a rig demo.
Yeah, it worked. I knew it didn't work because it came back in under 20 seconds. Yeah, now something happened. Okay, now let's do some interesting things. Let's add a D key, which is 1. Should this type check? Come on, core.typed. Will it type check? It does type check. And the reason it type checks is that this syntax here is short for mandatory entries. So you can have extra entries in a mandatory map. If you really do want a map with exactly 1 entry, you can use the complete true. Please give me complete. Thank you. The complete true. This says that this map is fully specified. So the mandatory entry Z is the only thing. Z.
That's really neat.
That is sexy.
Yeah. This checks it at compile time.
Correct. So let's. I'll prove that to you by getting rid of that. So nothing's being run. Oh wait, no, that is, yeah, this is returning a Z entry. Okay, so this was misleading. What I actually wanted to do was do this. Mandatory, complete, true. So this is a mandatory entry of Z, and then it's mapped to a 1 count map. or a single entry map. And we should get a glorious error message that takes up all the screen in 5. It's not that bad. Okay, so we're expecting an output. That's this part here. We're expecting an output, and I think it's pointing at this assoc, so this entire thing. What we're actually getting is a map with 2 mandatory entries, C and D, and we said it. There is 1 mandatory entry, and there are no extra entries. Okay. Any questions at this point? Okay.
Nope, but everyone thinks that's really cool.
Yeah.
Awesome, thank you. What else can you do with HMaps?
There was a question if you could turn off mandatory. Is there some other specification, like optional or?
Let's do it. Whoop, my parens. Come back. Okay. So there are many interesting combinations with. Let's make this look nicer.
I think if it's got a C.
Ambrose, you gotta check out par infer.
What? Par edit?
Par
Oh, I like
infer.
that.
It's the new thing.
I'll look it up. All right. What am I doing? Okay. Well, let's go back to a C. So this optional entry, it's either in the map or it's either not in the map. And notice that this is different, and I haven't mentioned this yet, but nil is its own value. So null is its own type, rather. It is different from Java, where if you write integer, you actually mean either null or integer. So this int here, it's a non-nullable int. So let's just, the difference between these 2 types is that this value is in that type, this value is in that type, and this value is in that type. The difference is with only these 2 values are in this type. So yeah, is that clear?
3 types.
Yeah, I think people are clear.
Yeah. Okay. So yeah, nil is its own thing, and one of the guarantees that type Clojure gives you is that if everything's typed and all the contracts are generated, then you won't get a null pointer exception. So null is tracked all of the time at compile time. And yeah, you can arbitrarily combine these things. Like this is a fully specified map that's either empty or it has a C entry, but it's not allowed any other entries. So yeah, there's expressivity there, and you can arbitrarily do merges and other interesting things. D1. So just to show that this actually works, let's go back to here.
No, I just had something with dynamically built types.
So we're associating a Z entry. Oh, this isn't going to work because this is going to have a Z and a D here, but we're saying it's inside. Oh, I've waited this long, I might as well wait. Okay, fine. Yeah. You have a Z entry and a D entry, but what we actually want is this. Oh. Will that work? That probably won't work. Let's just fix the annotation. Yeah. D int. Anyway, the point is you can do the normal things you do in Clojure, destructuring, assoc, merge, disoc, and it just type checked which is good news. The other natural extension is that you can type check keyword arguments, although there isn't a very good correspondence between keyword arguments and maps. So you can't reuse this input. I'll show you what I mean. So say you have two mandatory keyword arguments, A, which is an int, and B, which is an int. This should also type check. We'll call it G. And yeah, this A corresponds to this A here. We're going to type check. All right, it type checked. Anyway, here's the keyword arguments, H maps. We have heterogeneous vectors as well. So if you want, this is how you annotate a two-place vector. Sorry, not that. As in a int is. Let's make this a little easier to read. So 1, 2 is of type int. I think we have heterogeneous lists, but they're less interesting. But I've tried to support most of the major idioms in Enclosure. I guess maybe the last thing I'll talk about is the flow checking in Clojure. So let's write another function. Let's call it maybe H, takes in a number and checks if it's a number, and then increments it. Okay, yet again, maybe H, nil, int, let's just okay, so if we comment out this when, this could throw a null pointer exception. We could be incrementing nil. So ideally, in the next 10 seconds, we'll get type Clojure telling us that. Yeah, so inc has been macro expanded to this Clojure lang numbers inc, and it's expecting a number, and we're giving it a nillable int. So that's bad. So normal Clojure idiom is that we have a when expression that only goes down this branch if it's an integer, and if we require it again, what actually happens is when expressions understand what it means to check a variable. It basically means that if you're down the then branch, it's not nil and it's not false. Therefore, it has to be an int because it's crossed off this nil. So that's kind of the intuition that's going on there. That's my quick demo of what's called occurrence typing. It's a typed racket feature that I've stolen with great pride. And it's very cool.
Gotta steal from the best.
Oh yeah, if I wasn't clear, this entire project is about 95% stolen from typed racket. I can claim 5% novelty, which is, yeah.
That's enough for a new draw.
Yeah. All right, so any questions on maybe this code that I just wrote? All right, so I guess any parting questions before I go and do some grading.
Hooray!
Yeah, this is due tomorrow. It's, oh my God.
Yeah, super fun.
Yeah. But I like talking about.
You don't have any questions?
I had a question. Yeah. Why are you using Vim? Did you rewrite it in Clojure?
Did I write typed Clojure in Clojure?
No, I noticed that you were using Vim, right?
Oh, he's asking why you're using Vim.
Why I'm using Vim or what in Vim I'm using?
Why?
Don't
Don't answer
It's gonna be
Don't
bad.
answer it. Don't answer it.
Well, if there are any Vim users in the crowd, use Vim type Clojure and Vim Clojure, and there is also a plugin called Vim typed Clojure, which does some extra things, which now that I think about it, are completely broken. So don't use Vim typed Clojure at the moment. It used to be that it like popped up with like a list of type errors, and you could go to them. But now that type errors are actually runtime errors, don't worry, it doesn't work. And I love Emacs and Cursive and Vim. It's just this is what I do. So I apologize for anyone who was offended by what I just did.
No, I think it's all good.
Any other questions on my editor choice?
It's cool work. It's cool work.
No, very nice. Very interesting, Ambrose. Thank you so much.
All right, thank you. Yeah, thanks.
Well, thanks for joining us tonight, and really appreciate your time. And thank you.
Thanks a lot. All right, have a good evening, everyone. See ya.
Thanks. Bye.